Okay, so today I'm burning through some stuff because I don't like it. This is pretty much how I roll. There's a whole bunch of stuff that I omitted from this unit because I just don't like it. And so we're going to start here talking about inductive reasoning and what it is. So inductive reasoning is making a conclusion, coming to a conclusion, I need to be able to spell. Making a conclusion based on observations and patterns. Based on observations and patterns. So it's looking at the world and observing and seeing patterns and then saying, hey, I bet that's going to happen again because it's happened every day this week. It'll probably happen again. That's the sort of inductive reasoning. And so it's really just looking at patterns. A conjecture is kind of like a hypothesis. It's a concluding statement. A concluding statement reached using inductive reasoning. So we use inductive reasoning when we recognize patterns, and when we recognize enough patterns, we'll make a statement like, hey, it's going to rain again today. Okay, and so that is when we would make a conjecture. So a conjecture is sort of like a hypothesis about what's going to happen based on the stuff we've been seeing before. Okay, so we want to use our inductive reasoning skills to find the next 5 terms in the sequence and then write a conjecture. So I have a couple of numbers here: 38, 31, 24. 17, 10. 10? Why 10? Oh, interesting. So it's subtracting 7 each time? All right. Hey, that seems pretty consistent. All right. So then if that pattern continues, what's next? And then negative 11 and then negative 18. Okay. So you recognize the pattern very, very quickly there. So what is our conjecture? How do we get the next term?
Subtracting 7.
Okay. Subtract 7 to get the next term. Very good. So based on your recognition of a pattern, you were able to make a very good conjecture. Okay, pretty straightforward. Let's go down to number 3. Number 3, we have 1, 4, 9, 16. What do we think comes next? Is it? Well, this is only going up by 3.
Oh, it must be negative 4, which is 1.
Well, but this is by 3, and then here it's by 5, and then. Okay, so it's going up by odd. So 3. Here, 5, it's going up by 7. So 3, 5, 7, what would you expect the next one to be? 9. 9, that's 25. All right, 3, 5, 7, 9. Then what would it go up by? 11. Okay, 11 would be 36. That's interesting. 3, 5, 7, 9, 11. 13. So 13 by 13 would be 49. All right, and then so up by 15, okay, and a 15 to that would be 64. All right, and then we'd have to go up by 17. All right, what would 17 be? 70, 81. 81. Hey, that's really interesting. All right, well, what's our conjecture here?
It slowly increases by odd numbers.
Okay. It increases, the next term is generated by adding the next odd number? Something like that? Okay. All right, so to get the next term, add the next odd number, maybe? That'll work, I guess. The next odd number, it's not the same odd number, so it's the next odd number. Okay, well that's really interesting. You know what else though? This is not only adding consecutive odds, but that is kind of a cool thing. These are also very special kinds of numbers. 81's not even. 25.
They can be square rooted.
They're perfect squares. Very good. Yeah, they are perfect squares. So just in case you didn't see it, and this is a fine conjecture. It's totally true. But this is also 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and 9 squared. So it's just the term squared. Isn't that interesting, though, that you can get perfect squares, but you can also get them just by adding consecutive odd integers, which is kind of interesting. Okay. Okay, cool. So that's conjecture. We saw a pattern, and we can make a prediction based on that pattern that we see. Fantastic. So what we want to be careful of is when we use our inductive reasoning, that we want to be able to verify that our conjecture is true. Okay, we have to be able to verify, and we can do that by having a counterexample. A counterexample is an example that shows a conjecture is false. So it's really kind of interesting when we're talking about logic statements. It's easy to make blanket statements, and our job is to find only one counterexample, one thing that proves your statement that this is always the truth. I only have to find one thing to prove you wrong, okay? And so it's kind of an interesting thing when people make blanket statements and you're like, well, what about that? That's a counterexample. When you bring up a point that is clearly proving them wrong, that's called a counterexample, okay? And so we want to determine if a conjecture is true or false, and if it's false, we're going to provide a counterexample. Again, one reason it doesn't work is all we're looking for. The sum of any two consecutive integers. What are consecutive integers? One after the other. Very good. One after the other. So, for instance, we can try a couple and see. So, two consecutive integers might be 4 plus 5. So, two consecutive integers is always odd. The sum means add. So the sum of any two consecutive integers is always odd. So 4 plus 5 is 9. That's an odd number. Give me two more consecutive integers. We're testing this conjecture. 7 and 4? Those aren't consecutive. 7 and 8? 7 and 8 is consecutive. That means 15. That's odd. That's true. What about negative? Integers can be positive or negative. So let's see. Negative 3 plus negative 4, that's a negative 7. That's also odd. Okay. Does this seem to be true? 0 and 1, that's always good to test around 0 and 1. 0 and 1 is 1. That's odd. That's true. Okay. All right. Is this seeming to be true? pretty true. I can't test all of them, but I do believe that that is a true statement. Seems to be pretty true. Okay. Let's look at 8. The product of two, what's product? Multiplication, good. So multiplication, the product of two numbers is always larger than either number. The product of two numbers is always larger than either number. Let's see, so 1 times 2? 1 times 2 equals 2. The product is always larger than either number. Well, it's larger than the 1. Is it larger than 2? No. Well, that's false, absolutely. Good counterexample there. 2 is not larger than 2. So that's definitely false. And it says any two numbers, so we could even do like 4 times a half. What is 4 times a half? What's half of 4? 2. Well, that's clearly the product of two numbers is always larger than either number. 2 is not larger than 4, so that's a false statement as well. So here, these are examples of counterexamples. EXAMPLES. Both of these are great counterexamples. Right there. You can do 0, like 5 times 0, which is 0. Well, that's 0 is clearly not larger than both of those numbers. So that's definitely a false statement. All right. Let's look at 10. If the area of a rectangle is 6 meters squared, then the dimensions must be 2 meters by 3 meters. True or false? False. So how do we find area, though? Multiplication, length times width. So the area of a rectangle is length times width. So 2 by 3, 2 meters by 3 meters does give me an area of 6. That's true, but must it be 2 by 3? What else could it be? It could be 1 by 6, sure. 1 by 6 is also going to give us an area of 6 meters. So that is definitely false. We could have 1 meter by 6 meters. And in fact, it could be radical 6 times radical 6 meters. What's radical 6 times radical 6? 6. Interesting. Just throw that out there. Okay. All right. So counterexamples are kind of fun. You just get to test things and find a failure. That's what we're looking for, finding the failure. All right. Any questions on that? All right. So we're going to go to, turn the page. 2.2. Don't you love this? Isn't it great? Could you imagine doing like a whole homework on that stuff? I'd poke my eye out with a poker. Okay. I like it. Okay. So now we want to also talk about compound statements. Compound statements, you write them all the time in English. I went to the park and built a sandcastle. Compound statement, okay? And so we do the same thing in math, and we're going to talk about this stuff here. So a statement. A statement is a sentence that is either true or false. And whether it's true or false, this is called the truth value. And it's the basis of all of our computers, okay? So this whole section that we're talking about here at the beginning, they are truth values. This is called Boolean logic. Something is either true or false. That's ones and zeros in computer land, okay? So if it's true, it gets a 1. If it's false, it gets a 0. And everything our computers do is based on Boolean logic, whether it's true or false, okay? A 1 or a 0. We've all seen that stuff, okay? So we represent using letters like as P or Q. Those are going to form up our statements. We just use P and Q because we're lazy, okay? That's all. And instead of writing out a whole big long sentence, we'd rather just summarize with a P and a Q, all right? So, for example, we have this statement P is supplementary angles have a sum of 180 degrees. So our statement, our P statement is supplementary angles have a sum of 180 degrees. Is this true or false? True. That's absolutely true. We know the definition of supplementary. We know that it equals 180 degrees. So that's a true statement. So in computer land, that would give it a 1. True. Okay. Here we're just going to use T. To negate a statement, a negation of a statement has the opposite truth value, and it's shown by the symbol of a little tilde. We use that in Spanish a lot. And so this little symbol, this little squiggle, okay, it's a little squiggle, this little symbol means not. And so, for example, if I put a little not in front of my P statement, so this says not P, then I have to insert a not somewhere. Supplementary angles do not have a sum of 180 degrees. So that's what putting a little not symbol in front would do. We'd have to insert a not into our statement. Now, supplementary angles do not have a sum of 180. True or false? False. So you can see, originally it was a true statement. When we put a not in front of it, that must negate it. It must make it false, okay? All right. Compound statements are two or more statements joined by the words and or. And I love these two words. They are mathematical words that are really important to understand here. So the first one I want to talk about is the conjunction. The conjunction are statements joined by the word and. And again, we have a symbol for that. We write this as P and Q. This is the symbol for and. It kind of looks like an A, doesn't it? Do you see that? Okay. So that symbol means the word and. So it's important that you understand the symbol here. And so this is exactly what I said before. I went to the beach, that's my P statement, and I built a sandcastle, that's my Q statement. All right, so we like to abbreviate. All right, and is a very specific and. This compound statement, this conjunction, is only true when both P and Q are true. It's true when both statements are true. Very important here. For an and conjunction, for a conjunction to be true, both parts have to be true. Okay? If only one thing is true, the whole thing is not true. We have to be very careful. Now, the disjunction is a statement joined by the word or, and this one has much more flexibility. A disjunction is written as P or Q. You can see that the symbol has been flipped upside down, and again, so this symbol means or. Anytime you see that upside down, I guess it's like a V, kind of looks like a V, but that means or. So P or Q. P or Q, or means you can be one or the other. Like if you go to a restaurant, do you want fries or chips? Okay, technically you could get one or the other, or it could be both. Maybe. half and half, like half and half maybe, I don't know. Okay, so when we have an or statement, a disjunction, it's true when at least one statement is true, okay? So or is a lot easier to achieve, okay? An and statement is much more challenging. Everything has to be true, but an or statement, just one thing could be true, all right? So here we've got some examples, and this is really what we're focusing on today. So directions, write compound statements using the statements below and determine each truth value. There are 7 days in a week is the P statement. There are 7 days in a week. True or false? True. Okay, that is a true statement. That's good to know. That is a true statement. All right. Q. Statement Q says March has exactly 30 days. Does March have exactly 30 days? 30 days has September, April, June, and November. All the rest of 31. 30 days has September, April, June, and November. All the rest of 31. Does March have 30 days? No, it has 31 days. And so this, actually, Q, is a false statement, okay? It does not have exactly 30 days. It has 31 days. All right, and then let's see. Statement R, Halloween is on October 31st. True. Okay, very good. So that's a true statement right off the bat. So we can independently assess the truth of each little statement. So what happens when we create a compound statement? Is this a statement an and or an or statement? And. Again, that symbol means and. And so we're going to write this statement out. We're going to write our conjunction here. So we're going to write, there are 7 days in a week. And what word do we use? And. Q is March has exactly 30 days. All right, so there is our conjunction, and we said that statement P was true, and statement Q we discussed was false. What is the truth value of this conjunction, both together? False is correct. The total truth value is false. And an and statement, both things have to be true for the compound statement to be true. All right, let's see. Again, this is an and or an or statement? And, okay. All right, so Q is March has exactly 30 days. March has, whoops, there's no E on has exactly 30 days. And my R statement is Halloween is on October 31st. Halloween is on October 31st. All right, we said Q, 30 days has March, is false. And the R statement we know is true. What's the total truth value for our statement? Yeah, also false. Again, everything has to be true for an and statement to be true. So let's do the last one here. This is P and R. So the P statement is, there are 7 days in a week. There are 7 days in a week. And the R statement is Halloween is on October 31st. All right. Is P a true statement? Is R a true statement? Yes. Is the conjunction a true statement? Yes. Again, because both things are true is the only time we are going to get a true value out on our conjunction. Okay. Questions on that? All right. Okay, we're going to do just a couple more here. Let's look at number 5. I'm not going to write the statement now. Let's just look at our notation, okay? So, P, and what's this symbol? Or, on number 5. On number 5. So, P or R, what was P? What was our P statement?
7 days in a week.
There are 7 days in a week. Is that true or false? True. Or, and what's our R statement? Halloween is on October 31st. That's also true. All right, for or statements, are we true or false here? True, yeah. On an or statement, one or the other, or both, okay? So at least one thing has to be true for our total truth value to be true. What's going on with number 6?
That means it's not true, right?
Well, let's see. What was our... So that symbol does mean not. And here again is an or symbol. I'm going to write this one out so we can see how we would write that out. Let's see. The Q statement was March has exactly 30 days. What is not Q going to be? Yeah. March does not have exactly 30 days. Okay, huh? We knew the other one was false. What's this one? True, yeah, that one has to be true. All right, or R was Halloween. Halloween is on October 31st. And that one is true. All right, so true or true. And again, at least one of these is true, so the whole disjunction is true when we put them together. All right. Let's just do this last one, number 7. All right, this is not P or not R. How would we write not P out? What was our P statement? There are not 7 days in a week, all right? There are not 7 days in a week. Or, all right, so that is not P. There are not 7 days in a week, true or false? False statement, very good. And then, or let's see, not R. What would not? Halloween is not on October 31st. Halloween is not on October 31st. True or false? False. All right. The whole statement is false. Yes. On an or, one thing, at least one thing has to be true, and we don't have a true here anywhere, so it's definitely false. Okay? Does that make any sense to you?
Yes.
Okay. So when we put a not in front of it, if it was originally true, it's going to switch to false. Okay? It negates it, so it's the opposite. And so that's something you want to read carefully today when you do the delta math, because it's going to give you like P is true and R is true. What is not P or not R? Like, you know, so it's just symbols. And so you have to think, oh, it's going to be the opposite, and then figure that out from there. Okay? All right, ladies and gentlemen, that's all I got for you today. Let me get that delta math out for you.